All right, we're finally ready to now calculate angular orientation with the gyroscope data. Actually, you've done this in a previous homework. You've used a different method, a trapezoidal method, to integrate the gyroscope data over time. And so this should just really be a review of that, right? So as you know, right, we're getting angular rate out of the gyroscope in degrees per second. Right, the angular rate is the derivative of the angle with respect to time, right, that angular position. And so we can get that angular position back, or an estimate of it, by integrating the angular velocity, right? We'll assume then we have some initial value for theta at time t equals 0 when this starts running. And so we would initialize theta to whatever our robot's position was in. In this particular example, I've got my MPU 6050 sitting fairly level on a desktop surface. It's not moving when we'll start this. So my angle will be 0 for all the axes at this point. So they will all be zeros. All right. Now, the summation time, right, or the sampling time, then influences how well we capture the data. The more often we can sample the data, right, the faster we pull in this information, then our assumption that that rate or that change has been constant over that interval is more likely to be true. So the faster we sample, the better results we get. But we are limited to how fast we can sample, right, by how long it takes to our computer program to run, right? As we've seen in another lesson, then when we set up the configuration of this, that theoretically we can sample from the gyro at 8 kilohertz, right? We've seen that even 1 kilohertz can be difficult with our I2C communication. We have to turn on our fast clock, our 400 kHz clock, right? So in practical limitations, then, as you're running a lot of code on your Arduino, right, as you've got other sensors on there, you might be lucky if you're able to go out and query this about 200 hertz, 250 hertz. That should be fine, right? Down to around 100 hertz, if you get down to that level, you'll probably start introducing more error. So we probably want to at least try to go for a target of about 200 hertz. Like I said, when you put your whole robot together and you find out the speed that your code's running, then you'll know how fast you can sample it, right? And we've also learned then that we get what's called drift error, right? Because when we bring this up and we calibrate it, we have a zero offset bias. And that zero offset bias, that DC bias, then we try to calibrate and get rid of it, but some of that still exists. And as we sum these readings over time, we're summing in that bias and we're accumulating error, right? So that error is called drift. And what drift means is if you move around in the world, if you move the gyroscope around in the world or your sensor and you put it back in the original position, and you would expect to go back to your original orientation, but you'll see that you don't actually do that because of this drift error. Right? So I've got an example here in this Arduino sketch. Let me put this up on the screen. It's pretty similar, right, to the accelerometer sketch from lesson 9. I've got some macros here to turn on certain printing information. Right. Here in main, right, I'm going to keep track of the gyro position. So this is my accumulated position over time. Delta position, well, that's the displacement, right? That's from one time period to the next. Calculating the offset, we're going to store the readings that we get in the gyro rate, so the degrees per second readings. These help with our timers. Right, I'm going to actually start this up. Instead of 4 milliseconds of timing to start, so you can see things on the screen, I will just start with 2 measurements per second, right, for my sample interval. Right? We'll want to, of course, change that, but we're just doing that now to make things readable. So I've got this debug information turned on right here. It's just going to print out things to let us know when it's calibrating, when it's finished. Let's actually just run this. Turn on the serial monitor. All right. And so actually I'm going to clear the output. It had some garbage in there like it does. I'm going to reset. Try to clear it. All right. And clear output, reset board. All right, ready to calibrate, calibration's complete. I'll stop that. Right, and then we get the offset values that are calculated as part of the debug, right? I'm just checking to see what the values are before the offset, what they are after the offset, just to make sure that my logic there is correct. Right, I can do a quick check here. 11, if I add minus 20 to it, I get -9. Right, you can do that with all these others just to do a quick check that your math is correct. And then it starts printing out information about the change of position, what the actual position is. Let's turn off some of the debug stuff that we don't need to see, right? What it is before the offset and after the offset. So we'll turn all that off, and then we'll just leave on this print all gyro. So that's going to show, print all gyro is going to show us what the rate is. So let me just comment that out. So we're going to leave on print all gyro and print position, right? Well, here we'll go through the sketch then, right? When the calibration's done in our main while loop, I'm calculating an elapsed time, right? The elapsed time is the millis timer minus the start time that we recorded. If it's greater than or equal to the sample interval, which right now I have it at 500 milliseconds, then we go ahead and read the gyro information, right? I'm going to reset the counter immediately after we read this. And so sample count later on, if I just want to print out every so many because I have this running fast, that will control how often things get printed, right? We turned off the debug information. Here we're adjusting the rate information with the offset values because I've not stored those offset values in the registers. Here, now I'm scaling that. So we've got these updated values, right? These are 16-bit signed integers. We divide that by 131, right? That's the scaling factor that we've seen for the default configuration that's set in the gyro, right? And so when I divide that by 131, this gives me degrees per second units. So I multiply that times, well, this is in milliseconds, and I want to get degrees. So we've got to divide the milliseconds by 1,000 to make that units of seconds. So degrees per second times seconds gives us degrees. And so I store that in what I call the delta position. That's just the displacement, right? That's how much we've moved from the last time we took the reading. So print all gyro is just going to print out then that displacement information with 4 decimal points. So we can take a look at that. But I like to take a look at this data when I first write a program, when I first develop it. I want to take a look at the data. Does it seem reasonable? Right. And then we're going to update. So here is where the summation takes place. Once we've got our change of position, this is where we're accumulating that angle over time. And so we're going to update all 3 axes, right? Obviously, right, could have done this in one step. Right now, I've got it broken up simply because I want to see some of this information. Like I said, as I develop code, I like to be able to check things, right? Later on, right, as I had this more developed, like in this case, if I think this is working correctly, then chances are I want to make it more efficient, then I would start changing a few things. I'd get rid of this delta position and do this all in one, basically one line of code, right? Other thing is I made these double, so I wanted to be able to track some information beyond the decimal point. So here I am doing a static typecast to make this a double. Right. Dividing it by a double, I didn't want to have integer division going on, so I could capture that information to the right of the decimal point. So that's what I'm doing the typecast here for doubles. Right. And like I said, here where I'm printing the position, I was only printing every 100, right? Because if we take then a faster sample measurement where we print out the position, I just wanted to print every 100. I'm trying to remember if I uploaded that change. So we pop this open on the serial monitor. We'll still probably have to wait a second for the calibration to finish. Then we start getting that information. Right, so here, right, I'm still seeing what the raw data is. And then I'm seeing what the change in position is after we do the scaling. So this should be our angle, then in degrees, right? That's that displacement. Here, change in position, and then gyro position. This is where it's adding it on. Well, the first one, these two are going to be the same because I initialized everything to 0 originally in the angles. But you can see as this goes on then, now this had, actually coincidentally, this had a negative displacement, which was the same as the other. It ended up zeroing out the gyro position. Right? But as time goes on, we can see the gyro position is changing and accumulating. All right. So I'm going to turn off then the print all gyro. Right? I'm going to turn off the print position. I'm going to put this back to say 4 milliseconds. That's about 200 hertz sample rate. Or 250, 250. All right. And so what it's going to do now is it's just, here, let me upload. Right, this should just be plotting. I want to use the serial plotter. So let's just turn on the serial monitor to confirm that all we're getting is a comma separated stream of numbers. And did I turn everything off? I might have done that. I might have uncommented. Yes, we're not getting any output because I turned everything off. I just want to plot. Again, so remember with the serial plotter, we just want to send numbers and they need to be comma separated. Then the last number we send to the plotter, we actually then say, we give it a new line character so it knows it's the end. So like I said, if we just pop this up on the screen, right, we can see then, okay, we're getting these 3 comma separated values. And if we turn on the serial plotter now, all right, we start getting our data. All right, so like I said, my board is just sitting flat on the table right now. Let me turn on some video. All right, let me see if I can. Get this into camera range. All right. So you can see then, this is jumping around a little bit, probably because I'm not absolutely steady. One thing we know is that if we shake things up a bit, right? This is just the gyro, not the accelerometer. So there is some change. There is some change in orientation. Right, we can see that happening. You can start tilting things. Right. So what I don't like about this is I don't know the name of the signal. Right. And so I probably tilted something, right? I probably rotated about the x-axis here. Right. That might be about 30 degrees if you can see that. Oh. Be nice. I need to make a nice little rig that I can, like something with a 45-degree angle so we can show things. But right, if I start rotating this way, we see that orientation change. Rotate this way, we see this change. I'm going to put it back down flat on the surface where I had it before. And let's see if we come back to 0 after a while. And you can see, right, I'm not coming back to 0. Something thinks it's about 7 degrees. And actually, I don't know if my actual orientation is, it could be 7 degrees off. I mean, what I should really do with an experiment is probably outline, use a piece of tape or something to outline on my desk the orientation so I could put things back in the same way. But what we really want to see is here, I suspect then that this is our yaw angle, and yaw can't be measured very well simply with a gyroscope. We actually need something like a magnetometer. A compass is easier. I need to say a compass. I can't say the other. To measure then that change in magnetic field, that usually gives us a better yaw reading. Roll and pitch, we usually get a decent reading out of the gyroscope. Right? Not sure which is which here. This one is gravitating. They're all gravitating very slowly back towards 0. I mean, it's been quite a few seconds and you can see that they're slowly making their way back towards 0. It's taking a long time to get rid of that error that was summed, right, over that period in the gyro. Right, and those are the drift errors. All right, so that's just what I wanted you to see, right? Run that sketch, play with it. You can see those drift errors in the gyro, and we're going to Then next, right, you'll want to read the lesson on the complementary filter, lesson 11, and we're going to put that all together to see if we can get better orientation angles out of the gyro and accelerometer. So I'll see you in the next lesson as soon as I can get the menu back.